Lecture 21, Chemical Kinetics, Temperature Dependence and Reaction Mechanisms. In the previous lecture, we began to look at how temperature affects the rate of reaction. In the rate law, we saw that the rate of reaction is directly related to the rate constant, or lowercase k. It turns out that the rate constant is what is related to the temperature. This relationship can be described using the Arrhenius equation. That equation is given on the right-hand side of the screen next to a picture of Svante Arrhenius. In this equation, it says that K is equal to A times e to the minus e sub A over RT. In this equation, A is known as the pre-exponential term. R is the thermodynamic gas constant, which is 8.314 joules per mole times Kelvin, and T is the Kelvin temperature. E sub A is known as the activation energy for the reaction. We explain the activation energy using transition state theory, which states that in order for reactants to form products, those reactants must pass through a structure or form a structure called the transition state. The activation energy is the energy difference between this transition state and the energy of the reactants. We can use the transition state along with the energies of the reactants and products to draw a reaction profile, which shows the energy of reactants, products, and the transition state, which is shown on the top of a hill. Also shown in the reaction profile is the difference between the reactants energy and a transition state, which is the activation energy, and the delta H for the reaction, which is the energy difference between the reactants and products. For the reaction that we looked at in class, which is the isomerization of methyl isocyanine and acetonitrile, the reactant had a higher energy than the products, indicating that this reaction was exothermic. We can also show endothermic reactions by setting the reactant energy lower than the product energy. Now it's time to dissect the Arrhenius equation and really look at how temperature has an effect on the rate constant. We first look at the exponential term. We call this exponential term a Boltzmann factor. Boltzmann's factors always have units of e to the energy over temperature. The Boltzmann factor represents the fraction of molecules that have enough energy to reach the transition state structure. We can show this by looking at Maxwell-Boltzmann distributions. Maxwell-Boltzmann distributions show the fraction of molecules as a function of kinetic energy. Therefore, it's showing the distribution of kinetic energies for a sample. The spread of the molecular energies depends on temperature, as well as the highest fraction of molecules with a certain kinetic energy, which is represented by the peak in the distribution. In the picture to the right, we show that the red curve, which represents T2, is at a higher temperature than T1. We know this because the distribution of kinetic energies is higher, and the most probable kinetic energy, which is represented by the peak of the curve, is at a higher kinetic energy than for the blue curve, which represents the distribution of kinetic energies at a lower temperature. Also shown on this plot is a dashed line that represents the activation energy for a given reaction. All of the kinetic energies, molecules with kinetic energies to the right or at higher energies than the activation energy, are those molecules that have enough energy to reach the transition state structure. We take those number of molecules as the area under the curve. The area under the red curve is higher than the area under the blue curve, indicating that more molecules at temperature T2, the higher temperature, have enough energy to reach the transition state structure. We can also depend the fraction of molecules that can surmount the activation barrier also decreases as the activation energy increases. If we move the dashed line that represents the activation energy, that means that less molecules will have enough energy to reach the transition state structure. Take-home point here is that as temperature increases, more molecules have enough energy to reach the transition state structure. Therefore, the reaction will occur at a higher rate. Another take on looking at the Arrhenius equation is looking at collision theory. Collision theory has a very basic premise. That premise is that molecules must collide with one another to make products. We can use collision theory to actually take a look at the pre-exponential term A. We see that A depends on two factors. The first factor is the collision frequency, which is denoted by a capital Z. The collision frequency represents the number of molecules that collide at a given time interval. Molecules will collide more frequently with one another at higher temperatures, which makes the rate of reaction a lot higher. The second term is called the orientation or steric factor and is given the symbol Greek letter rho. The steric factor also takes into effect that the collisions must be effective, or that the molecules must be oriented in a correct way to form products. Here's an example: the reaction between NO2Cl and Cl, forming NO2 and Cl2. This first example shows an ineffective collision. That is, the NO2Cl molecule is not pointing in the correct orientation to form products. So the molecules collide, but no reaction takes place. The second row represents an effective collision, where the NO2Cl molecule is pointing in the correct direction, having the chlorine atoms facing one another. Now when the collision takes place, the chlorine atoms bond to one another, and a chlorine molecule is formed, leaving NO2 behind. This collision was effective because the molecules were pointing in the correct orientation. Therefore, the take-home point here is that the pre-exponential factor takes into account how the molecules collide. Molecules must collide frequently with one another, and we need to have a high fraction of molecules that have effective collisions. Figuring out the collision factor and the orientation factor really depends on looking at pre-existing experimental data. The Arrhenius equation has a few uses. Experimentally, we can collect rate constants at different temperatures. This data can be plotted using the Arrhenius equation by if we take the natural log of both sides of the equation. This gives an equation that can be mapped towards to the equation of a best fit line. The plot on the right shows that if we plot the natural log of the rate constant as a function of 1 over temperature for the decomposition of ozone, we find that the slope of the line is equal to minus activation energy over R. And the y-intercept is equal to the natural log of the pre-exponential term. Therefore, plotting rate constant data at different temperatures allows us to get the activation energy and the pre-exponential factor experimentally. What's more useful for us is to just compare two rate constants at two different temperatures. This two-point Arrhenius equation, which is shown on the right, allows us to calculate the activation energy if we know two rate constants at two different temperatures. If we know the activation energy and the rate constant at one temperature, we can find the rate constant for the same reaction at a different temperature. Here's an example of a problem using this two-point Arrhenius equation. We have two rate constants for the decomposition of ozone, which was shown on the previous slide. One rate constant at 600 degrees Kelvin and one rate constant at 800 degrees Kelvin. We want to use this information to calculate the activation energy, E sub A, for the decomposition of ozone. To do this problem, we definitely want to make sure that we keep the data straight. That is, keeping K2 and T2 together and K1 and T1 together. We let K1 be the rate constant at 600 degrees Kelvin and K2 to be the rate constant at 800 degrees Kelvin. We therefore take our two-point Arrhenius equation in the box and substitute in the rate constants and temperatures. We also put in R, which again we want to use 8.314 joules per mole times Kelvin. The next step shows that we take the natural log of the rate constant ratio, yielding a unitless quantity. We also take the difference between 1 over the temperature, which also gives us a value with units of inverse Kelvin. We now want to combine the difference between 1 over temperature with R by division. So we divide the difference between the 1 over temperature by the rate constant, yielding our third line. To get our activation energy, we divide the ratio between the rate constants divided by the number on the right. This gives us an activation energy of 9.31 times 10 to the fourth joules per mole. Typically, activation energies are given in kilojoules per mole, so we can convert that to kilojoules per mole by dividing our E sub A by 1,000. This gives us a final activation energy of 93.1 kilojoules per mole. The next part of our lecture, we're going to take a look at reaction mechanisms. Reaction mechanisms show how the reaction takes place in a series of molecular steps that we call elementary reactions. In general chemistry, we'll look at very simple reaction mechanisms that may have 2 to 4 steps. There are very complicated reaction mechanisms, such as the mechanism involved in photosynthesis, the conversion of carbon dioxide and water into sugar and oxygen gas. This is a multi-step complicated process that also depends on kinetics. However, the basic ideas are the same. In a reaction mechanism has a series of individual molecular steps known as elementary reactions. Elementary reactions represent simple molecular collisions, and they occur exactly as written, meaning they show an actual collision or rearrangement or decomposition of a molecule. Reaction mechanisms can be characterized by the number of molecules that take place in the collision or interaction. We call this the molecularity of the elementary reaction. Another thing that distinguishes an elementary reaction from an overall reaction is that elementary reactions can have rate laws written for them. Remember, earlier in this unit, we said that we cannot write rate laws directly from an equation for a reaction. However, we can do this for an elementary reaction. If you're worried about how you'll tell the difference, remember that elementary reactions usually come in sets. Here are 3 types of elementary reactions. We have unimolecular reactions in which only one reactant appears on the left-hand side of the elementary reaction. This could be a molecule that rearranges or decomposes to form products. We can also have bimolecular elementary reactions where 2 molecules collide to form products. Those 2 molecules can be the same or they can be different. The third type that you might see are termolecular elementary reactions, where 3 molecules collide to form products. Again, those molecules could all be the same or they could all be different and anything in between. Termolecular elementary reactions are very rare because it's very unlikely that 3 things will collide with one another and actually form products, and are usually not proposed. In an elementary reaction, you may see reactant species and product species that appear in the overall reaction. You may also see reactive intermediates. Reactive intermediates are species that are formed in one elementary reaction and are usually used up in a second elementary reaction. Reactive intermediates tend to be what we call metastable or relatively unstable and cannot be isolated. On the right shows an example of a simple 2-step reaction. For the reaction A plus B gives C plus D. In step 2, A plus B collide to form the reactive intermediate AB. And then the second step shows that the reactive intermediate is then decomposes to form C plus D. If you look at the energy profile, it shows the relative energy between the reactants, A plus B, products, C plus D, and the reactive intermediate. Note that the reactive intermediate has the highest energy on the reaction profile. When looking at a reaction mechanism, multi-step reaction mechanism, you can note that in order for that mechanism to be valid, all of the elementary reactions must add up to give the overall reaction. This means that all reactive intermediates must cancel out to give the overall reaction. This is a very convenient way to check whether or not the reaction mechanism is valid. Note that in the reaction mechanism on the right, I denoted each step as being slow or fast. Step 1 is a slow step, and step 2 is a fast step. If you look at the reaction profile, you can see why. The activation energy for step 1, which is AB, goes to the reactive intermediate AB. Notice that the activation energy for that step is a lot larger than the activation energy for the second step. This means that this reaction will occur more slowly because it takes more energy to get to the first transition state. We call this slow step the rate limiting step or the rate determining step. This is the step that occurs the slowest and will therefore most closely affect the rate of reaction. Therefore, we always say that the overall rate law for the reaction most closely resembles the rate law for the slow step. You can think of this as a traffic bottleneck. If on your commute to work or school has an accident that occurred on a Parkway West in Pittsburgh, we know that the area of the accident will be the bottleneck. It'll be this part of your commute that takes the longest to get through. This is the same idea with a rate determining step. The slow step will determine mostly how fast the reaction occurs. Reaction mechanisms are usually theoretically proposed after a lot of data is collected about the reaction, which requires many experiments. One way to tell if your reaction mechanism is a valid one is to try to determine the rate law for your overall reaction using the reaction mechanism. There are two cases that we'll look for specifically in this class. We will look at where a reaction mechanism where the first step of the mechanism is a slow step. We'll also look at reaction mechanisms where the first step is a fast equilibrium step, and the slow step is a second or subsequent reaction step. Let's look at the first case because it's the easiest to figure out a rate law for. We'll do this by looking at this example, which we've seen before. The isomerization of cyclopropane to form propene. We propose a two-step mechanism for this reaction. The first step is a bimolecular step where two cyclopropene molecules collide with one another. During this collision, some kinetic energy is transferred from one molecule to another molecule, forming a cyclopropane molecule that has some extra kinetic energy. Notice that this elementary reaction is not balanced, which is something that can happen if we look at reaction mechanisms. Elementary reactions are not required to be balanced. The asterisk tells us that this molecule has more kinetic energy than it previously did. The second step, which is the fast step, is that excited cyclopropane molecule now has enough energy to rearrange to form propene. We want to know what the rate law is for this overall reaction. The first thing to realize is that the rate law is always going to depend mainly on the slow step or the rate limiting step. In this mechanism, the first step is the slow step. So we write a rate law for that elementary reaction, which is rate is equal to the rate constant for that reaction, K1, times the concentration of cyclopropane squared. If we look at this rate law, we notice that no reactive intermediates appear in the rate law, just reactants. This is good because we can actually manipulate the amounts of reactants. We don't want a rate law that has reactive intermediates in it. This also means that in this case, the rate law for the slow step can be the overall rate law, since it does not have any reactive intermediates. So for this reaction, the rate law is the same rate law as for the slow step. That is, that rate is equal to K1 times the concentration of cyclopropane squared. We can generalize this for other reactions with a slow initial step. That any time a reaction has a slow initial step, the rate law for that slow elementary reaction will equal the rate law for the overall reaction. Now let's look at the second case, which is a little bit more complicated. If the first step is not the slow step, we might need to do some manipulations to make sure that no reactive intermediates appear in our rate law. We can use a shortcut learned from equilibrium. One of the conditions for a reaction to reach equilibrium is that the rate for the forward reaction must equal the rate for the reverse reaction. We can use this to use a previous step that's a fast equilibrium step to actually rewrite the concentration of a reactive intermediate in a form that includes just the concentrations of the reactants. Here's an example. We have a general mechanism, two-step mechanism, where the first elementary reaction is a fast equilibrium reaction, and the second is a slow reaction. We notice that the rate law, note that the rate law always, for the overall reaction, always resembles the rate law for the slow step. Therefore, we write the rate law for the slow step as rate is equal to K2 times the concentration of AB, where K2 is the rate constant for the second elementary reaction. AB is a reactive intermediate. Therefore, we cannot control its concentration once a reaction proceeds. And we want to rewrite that rate law in terms of the reactants so that it can be the overall rate law for the reaction. Remembering that for the first step, which is an equilibrium step, that when that step reaches equilibrium, the rate for the forward reaction will equal the rate for the backwards reaction. Therefore, we use the first step in our mechanism to write the rate law for the forward reaction, which is K1 times concentration of A times the concentration of B, is equal to the rate law for the backwards reaction, which is K minus 1 times the concentration of AB. K1 is the rate constant for the forward reaction, and K minus 1 is the rate constant for the backwards reaction. If we rearrange this equation to solve for A times B, we get that the concentration of AB is equal to K1 divided by K minus 1 times the concentration of A times the concentration of B. We now have an expression that relates the concentration of the reactive intermediate to the concentration of the reactants themselves. We now take this expression and substitute it into the rate law for the slow step. This gives us that the rate is equal to K2 times K1 over K minus 1 times the concentration of A times the concentration of B. This rate law is our overall rate law. Note that it now does not include any reactive intermediates and only depends on the reactants. Therefore, we use the first step, the equilibrium step, to determine the concentration, how to write the concentration of the reactive intermediate in terms of reactants. The combination of rate constants end up equaling the overall rate constant. We're not going to focus too much on the combination of these constants. Now let's do an example with real chemicals. Here's a reaction between NO and oxygen to form NO2. This reaction has a two-step mechanism where the first step of the mechanism is a fast equilibrium step, and the second elementary reaction is the slow step, or the rate determining step. We want to use this mechanism now to figure out the overall reaction, the overall rate law. Once again, we note that the slow step will always determine the rate law for the reaction. The rate law for the slow step is rate is equal to K2 times the concentration of NO2 times the concentration, NO3 times the concentration of NO. We note that NO3 is a reactive intermediate, and therefore we cannot have this NO3 in our overall rate law. To express it in terms of reactants, we use the first step, which is a fast equilibrium, and set the rate of the forward reaction equal to the rate of the reverse reaction. We write rate laws, therefore, for the forward and reverse reaction and set them equal to one another. This gives us that K1 times the concentration of NO times the concentration of O2 is equal to K minus 1 times the concentration of NO3. If we rearrange just to solve for the concentration of the reactive intermediate, NO3, we get that the concentration of NO3 is equal to K1 divided by K minus 1 times the concentration of NO times the concentration of O2. We now take this and substitute it into our rate law for the slow step. This gives us that rate is equal to the equal to K1 times K2 divided by K minus 1 times the concentration of NO times the concentration of O2 times the concentration of NO. We can combine those two concentrations of NO to give us NO squared, giving us the final rate law as rate is equal to K2 times K1 over K minus 1 times the concentration of NO2 squared times the concentration of O2.